Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulation of nonlinear control systems. Today we are going to discuss the robust non-singular terminal sliding mode control for nonlinear magnetic bearing system. I've looked into this paper and I have tried to simulate the control that has been presented in this paper. I have been able to successfully get some simulation results, but some of the results are not yet satisfactory. I will show you how I have approached simulation of the control presented in this paper, and then you can use this video as a starting point if you want to do further research on the robust non-singular terminal sliding mode control. So basically the magnetic bearing system that has been discussed in this paper is the thrust active magnetic bearing system, and the reason why non-singular terminal sliding mode control has been proposed is to avoid the singularity problem in the usual terminal sliding mode control. And then they also have used the recurrent Hermite neural networks to estimate the uncertainties in the system. Okay, so this is the system where there is a thrust disk and the rotor, and there are two electromagnets, the lower electromagnet and the upper electromagnet, and there are some the proposed control laws are applied in the form of voltages which result in the currents in the coil, which basically produce the magnetic force that is used for control purposes. The model of magnetic bearing system is very simple. It's basically a second order system which is presented by, let's say, this equation 5 is a good representation of the system. Z double dot is A times Z dot plus B times Z plus G times U plus some disturbance. In this video I'm just going to ignore this disturbance. You can add disturbance later on. So A is simply minus C over M, it's a constant, and the B is kz over m, is again a constant. G is ki over m, again constant, and D disturbance can be a function of time. So where this comes from is basically this is the force equation which is based on the currents, and they have converted this equation into a simplified form which I just described for you. They also propose that you can model lumped uncertainties in the system in this manner, that the Z double dot is A nominal times C dot plus B nominal times Z plus G nominal times U plus L for lumped uncertainties, which could be a function of time. Then lumped uncertainties are assumed to be bounded by this constant delta, as usual, as we do for all the sliding mode control designs. Error is Z is the displacement and Z dot is the rate of change of displacement, and this figure basically tells you exactly the distance here is Z naught minus Z, and this is Z naught plus Z. So Z naught is a constant, but Z is basically what measures the displacement. And then the first very simple control law that we are going to discuss is basically presented at the end of the paper. This is the PID control law: Kp times error plus Ki times integral of error plus Kd times the derivative of the error. If I go to the MATLAB, these are the parameters: m, the mass, kz, ki, C. These are the constants for the system which are given in the paper here. So mass, value of mass, this voltage we are not going to use because we are not doing experiments on the real system. We just need the control force U. So for that we need K, Z, Ki and this small c here. So these values have been put in the code, and the system is the same as equation 6. I go back to that. So this is the system in my code. So if you see, Zm is the desirable value of this is the signal that is to be tracked by the displacement. So this is Zm is sine of t, and then Zmd is the derivative of sine t, which is cos t, and then error is defined as Zm minus x1. X1 is our first state variable, which is equal to z, and the derivative of error is ed, which is Zmd minus x2. Kp, Kd and Ki values are given in this paper in the same table that I have shown you. So A is equal to minus C over M. This is given here in the paper. A is equal to minus C over M. B is equal to K Z over M. So these are the K. G is equal to Ki over M. So these are the same things that are given in the paper. U is equal to Kp times error plus Kd times derivative of error plus Ki times x3 is the basically integral state. The derivative of x3 is equal to error. That means that the x3 state is equal to the integral of error. Then this is the PID control, and this x1 dot is equal to x2 and x2 dot is equal to, like this is z dot is equal to the second state, and the z double dot is equal to the derivative of the second state, and the first state is z itself. So this equation is the same as equation 5 with zero disturbance. And if I go and run this equation using the script file, so this ODE45 function calls, let me just comment this we will use later. This will call bearing PID, which is the name of the file here. So this is bearing PID function name, which will be called by this file here. We will run it for 10 seconds and we'll start with zero initial conditions, and then we will plot the first state variable, which is z, versus sine t, which is the desirable value of z, and then we will also plot the difference between the two things, the z and its desirable value, which will be the tracking error. So if we run this file, we get the results. So these are the results. You can see that the error is the magnitude of error is 0.1 millimeter. So the units of displacement in this paper are millimeters. All the constant values are given accordingly. So the error, so this here blue line is the actual value of the z state, and the red dotted line is the desirable value of the state. So you can see that the state tracking is there, but there are some undershoots and overshoots involved in the tracking of the desirable trajectory. These can be avoided by tuning of the gains. I have not tried to tune the gains. If you want to make the PID perform better, you can try to improve the gains of Kp, Ki, Kd. So I'm using Kp 15, Kd 0.05 and Ki is equal to 10. You can try different values to improve this performance of the PID control. Next we shall be discussing the sliding mode control for the same system. Its equation is also given at the end of the paper. This equation 34, this is the equation for simple sliding mode control, and I will show you how this works. So in sliding mode control, there is obviously a sliding surface, which is defined as S is equal to derivative of the error plus lambda times error. Lambda is a positive constant, and then based on the sliding surface, the sliding mode control is 1 over g, times the second derivative of the desirable value of z, which is zm double dot, minus an times z dot minus bn times z, which is the cancellation of the model terms, then lambda times derivative of the error plus delta times saturation of this sliding surface divided by this phi, and the value of phi and delta are given in the, and lambda are given in this table. So here for sliding mode control, lambda is 1.8, delta is 2.5, phi is 0.01. So we go to the coding of this. So this is the code for sliding mode control for bearing system. So all these constants are the same. Lambda is equal to 1.8, delta is equal to 2.5, phi is equal to 0.01. Desirable value of z is sine t, and its derivative is cos t, and double derivative is minus sine t. The error is given by zm minus x1, and the derivative of error is zm derivative minus x2, which is the derivative. X2 is the derivative of x1, remember that. This is the sliding surface, the derivative of error plus lambda times error, and then this if else is used for the for implementation of this saturation function. So saturation function is implemented in such a way that if s is greater than phi, then saturation of s is equal to sine of s, and else saturation of s is equal to s over phi. This has been suggested by this paper itself, and again this model is the same as the one used in the PID controller, except for this control equation, that is the one given in the paper here. So, and then if we run this, let's suppose so this is bearing SMC. So if we run this file, so instead of this file, comment this and uncomment this. So if we run bearing SMC, then we can see the results. So you can see here that the error very smoothly, the maximum value is minus 0.14, and the error goes to 0. And here are the results of reference tracking. You see here the reference tracking is much better compared to the PID, but again PID I would based on my experience, I really think that if you tune the PID, you might be able to get better result from PID. But this is the result from sliding mode control on the bearing magnetic bearing system. So the tracking is almost perfect with some initial error. And yeah, similarly we can go on. So these are the two controls that I would really emphasize for you to use if you want to control a magnetic bearing system of the sort that has been presented in this paper. The other controllers, I have had some success in implementing them, but due to some highly I would say tricky equations, it is very difficult to get reasonable or sensible results. For example, in the so this is what I was talking about. Saturation of S is equal to sine of S when S is greater than phi, and S over phi when S is less than phi. So this is what we have implemented for P. So here, this, for example, this terminal sliding mode control law, this I have also simulated this. So for example, if you go to here, and this is the so this was the code for simple sliding mode control. And again, if you want this code, please take a screenshot of the video and type the code by yourself. this code is clearly visible on your screen, so there is no reason for you can pause the video right here and type the code on your MATLAB by yourself. So here this is the code for again the constants are defined in the same way, the derivative of ZM are defined in the same way, error is the same, so this is the same thing. The sliding surface is now different. This is the first major difference. The sliding surface for terminal sliding mode control, that is the derivative of error plus lambda times error raised to the power q over p. This is what makes things very tricky, because when you take error raised to the power q over p and the q is equal to, like, q and p have certain so this is the condition for q and p. P should be greater than q but less than 2 times q. If as long as this condition holds, then the paper claims that all things will be well. But this e raised to the error raised to the power q over p, that creates a lot of problems, and at least for me. So I have not investigated this in detail, because magnetic bearing control is not really something I do for my own research. This is just something I'm doing for the community. So still I want to give you, like, at least the starting point, which is I recommend you start from the PID control and the SMC control discussed in this paper, but I will continue discussion briefly about the terminal sliding mode control. So the difference is in the sliding surface, and the second difference is in the control law. So in the control law, see that the here G inverse ZM double dot, so A and B, and these are the similar terms that appeared in the previous sliding mode control, but there you have a term related to error and its raised power and multiplied by the derivative of the error. So this terminal sliding mode control is a little bit more complex as compared to the simple sliding mode control, but anyways, we can run this and we can just use, instead of SMC, we run this TSMC, because the file name of the terminal sliding mode is bearing TSMC. So we run this file, and so apparently we get a very good looking result, that the error in the simple SMC was going to minus 0.14, and this is less than minus 0.1. And if you look at the tracking, it looks almost like, it looks great. But the problem that I have seen here is that there are some warnings from the MATLAB that some of the values are imaginary. For example, if I do this x, so this is, so you can see there are some the imaginary part is almost zero here, almost zero. I mean it's probably all zero, but I don't know, MATLAB is having some difficulty in recognizing this z with the terminal sliding mode control as a real variable, whereas if you go to, instead of terminal sliding mode control, if I run the simple sliding mode control, then in this case the error goes to almost minus 0.14, but the x is, here this is a real number, it has no imaginary part. So that's the difference that I wanted to bring your attention to, the difference between the sliding mode control and the terminal sliding mode control. So next we are going to discuss the non-singular terminal. See, this warning was not here in case of terminal sliding mode control. So next we go to the here, so far So now we have discussed this terminal sliding mode control. Next is the non-singular terminal sliding mode control. The difference between the terminal sliding mode control and the non-singular terminal sliding mode control is, again, in terminal sliding mode control, the sliding surface is the derivative of error plus lambda times error raised to the power q over p, whereas in non-singular terminal sliding mode control, the sliding surface is a little bit different, which is probably this is. So this is error plus 1 over lambda times error, the derivative. Now in the terminal sliding mode control, the error e has raised to the power p over q, but in the non-singular terminal sliding mode control, the derivative of the error has raised to the power p over q. So this is the difference here. Instead of error having power p over q, now the derivative of error is having power p over q, and this difference in sliding surface as well as the control law is almost the same. You can see here that z double dot minus a and z b, and there is this difference in the control law. This term is different. The fourth term in the control law is different. Fifth term is the same. So there is this difference. So if you go to the code, this is bearing NT SMC. So this is bearing NT SMC, non-singular terminal sliding mode control. And these are all, again, this code is all the same, except that this sliding surface is now the power raised to the power p over q is for the derivative of the error instead of the error. And there in the control law, this fourth term is different compared to this terminal sliding mode control, where the raised power is for error, and a derivative of error has no raised, it's like raised to the power 1. And if we go like so these are the same dynamics of the system. I have not included any uncertainty. So if you run this using the same file, so instead of bearing TSMC, we have bearing NTSMC. And if we run bearing NTSMC, you can see here the error is even smaller than the bearing and bearing SMC. I think, yeah, it is 0.09. So it's almost I mean, it looks very good performance, but again there is just like the TSMC, there are some warnings and there are some imaginary. So this imaginary part, you can see here 0.0000. So it means that imaginary part is almost 0, but I don't know why MATLAB is having this sort of a problem here. But anyways, this is the non-singular terminal sliding mode control for you for the magnetic bearing system. And last but not the least, of course, we will discuss the terminal non-singular terminal sliding mode control with robust part and the neural networks. So neural networks, I have one previous video on neural networks which involved the sliding mode control with the RBF neural networks. So these are the Hermite polynomial based neural networks. The RBF neural networks are based on some slightly different polynomial. I will share the link of that video as well, because in that video I had more success with implementation of neural networks compared to this video, because this neural network is tricky due to just one reason. The reason is that the neuron theta, that is depending upon the weight from the previous cycle n-1. Well, you cannot understand this, we have to start from the beginning. So the neural network output is weights times these gamma variables. So gamma is given by some nonlinear function of this theta neurons. So h is the activation function for each hidden neuron. This is given by 1 over square root of 2 raised to the power j into j factorial under root pi times exponent of minus theta j square. This capital N is for iteration number. So of course training of neural network is iterative process. So hj is given by this Hermite polynomial defined by this complicated equation, and I have implemented all of this in the code given here. You can, this code is available right now. It's on your screens in a single shot. It's a 32 line code, and I have deliberately made it to fit in one screen so that you can pause the video and copy this code. Although this code does not it does not work properly, because I will show you how much does it work, and then you can. But first I have to explain that in this code we have this usual system x1 dot x2 dot, but we also have some extra state variables for the middle for the hidden layer of the neural network. So layer 2 of the neural network will give us this w dot. W dot is, in this paper they have used 9 of these weights like w's. So we have 9 state variables corresponding to these w's, and 1 extra state variable corresponding to this epsilon. And if you look into this code, we have this epsilon x3 is I have selected x3 to be epsilon. So this equation epsilon dot is the same as equation 29 in the paper, and w dot is the equation. This is actually one line for 9 equations, because gm and w are the vectors of 9 cross 1, and this is this equation. And then the sliding surface is the same that is used in the non-singular terminal sliding mode control. Then this is the code that I have implemented for calculation of the gammas, because it is very complicated, and you also have to use this global variable gamma, and for gamma n minus 1. So thetas are basically error plus error derivative plus this gamma times capital gamma n minus 1. Capital gamma n minus 1 is the previous value of gamma. In order to retain the previous value of gamma, you have to define the global variable, which is a complicated thing. And then you have to, when you call this function, so in order to call this function, you need to, so this function will have like you have to define the global variable here as well. With the 9 cross 1, you can initiate with the zeros, and then if you run this file, so if you have like, this is the error. So it starts from 0 and it goes to 0.4, which is a very large value. It comes back to 0, but then it overshoots, and then the simulation doesn't even complete for full 10 seconds. Because the calculations, this is the actual value which tries to converge to the desirable value. So I don't think these results are accurate. Of course they are not accurate. I have tried to implement this code, but this does not work. You can take this as a starting point, study the paper. If you want, you can try to find errors in the code, or maybe there are some errors in the paper. It's very unlikely that there are errors in the paper, because it's a paper published in the IEEE Transactions on Control Systems Technology. It's a very highly reputed journal, so there's a very less chance that there are errors in the paper. Most definitely I have some misunderstanding in the code, so I don't really have time to look into that, but I still want to share it for those who want to do further research on this topic. That's it. Thank you for watching.